We would like to start. Thank you. Before Haim will start, I would like to say a few words. This year, the university was supposed to celebrate 100 years for her inauguration, existence. And the celebration was meant to be on 13 June. We all know what happened in June 13. And everything that was planned was canceled. One of the things that we are planning was to celebrate the great prize, the brain prize of Haim Sompolinsky. And we did something with a lot of love, with the help of the family. So I would like to show you a little bit of what we have done, and then I will have the place for Haim. So we will begin with me.
From a broad field of strong nominations from all over the world, the selection committee is awarding this year's Brain Prize to 3 scientists for their foundational work in theoretical and computational neuroscience. The Brain Prize 2024 goes to Professor Terry Sanowski, Professor Larry Abbott, and Professor Haim Sompolinsky.
We are living in an era of remarkable transformation, led by a powerful technology. A technology capable of mimicking the workings of the human brain that is reshaping our world in ways we couldn't have imagined even a decade ago. It writes, it sees, it even diagnoses diseases. Many paths led to this world-changing technological revolution. One of them is the remarkable story of how research into the human brain paved the way for what we now know as artificial intelligence.
The group of us were drawn by the mystery of the brain and the importance of making progress. Every thought that passes through our mind, every decision that we make, every movement that we make involves the concerted effort of large populations of neurons. So it is impossible to understand how this emerges without the tools and the concept of physics.
Physicists had a long tradition of developing theories and models of things that are hard to measure or experiment on directly. The most groundbreaking models of the brain were artificial neural networks. With these, scientists could start figuring out how billions of neurons in the brain work together. These artificial neural networks could mimic functions of the human brain, like how we generate speech.
Haim Sompolinsky also has a background in physics, and he's built models of the collective behavior of large numbers of neurons to try to understand their dynamic activity and how they actually go about solving a whole range of problems in perception and memory and in action as well.
The brain is enormous in the complexity of its microscopic structure. The more we learn about the brain, the more we are at awe about that complexity. I see AI as a major revolution, not only in technology, but also in potentially new ways to understand the brain.
I think it's absolutely fantastic that physicists are taking an interest in the brain, because they're bringing models with a degree of quantitative precision that we've not seen before. And Haim has been at the center of that development within our subject.
My father, he worked as a scientist. His bookshelf was completely chaotic mix of books on the Jewish law, on the Torah, a book on the integral and differential mathematics, or some encyclopedia. That was the kind of spirit at our home, and this is the legacy that he left for me. When I finished my PhD in physics, I went to Harvard. I was looking for problems which are poorly understood, where I can really make an impact. I decided to focus on spin glasses. So my studies of these structures revealed the world of physics of disordered systems. And that really initiated my entry into neural networks and the mystery of the brain. The first stage of that career change left us more or less isolated. Physicists saw what we did as not physics but biology. And biologists were wondering what physicists have to do in neuroscience. When we started transitioning to neuroscience, we formed a coalition of researchers from the medical school, from the life science, mathematicians. The terminology was different, and we spent considerable effort to, first of all, establish a common language. The interactions between AI and neuroscience is going to be very fruitful and productive from both sides. I hope that what we will see in the future is AI for the brain diseases. The Brain Prize is a recognition of the field, recognition of the important role of theory and computation in understanding the brain.
Thank you. You can kill me later, Haim.
Now for the science. Okay, so hope you are all satiated and happy and relaxed. And for the main course, we have Professor Haim Sompolinsky, which as you already seen is a renowned scientist. Haim is a professor at Hebrew University, both at the physics department and also at LSEC. And he's also a professor at Harvard University. And I'm happy that he's also a colleague and a friend. And without further ado.
As you all know, there is no free will, so I'm very embarrassed and apologize for that. Orit, come to see me. Okay, very good. Okay, so this is the title of my talk, Artificial Agents, Perils and Promise of a New Intelligent Species. As you will see, there is really a serious content in calling AI intelligent species. That's what the goal of my talk is, to convince you that there is something serious about AI beyond just conversational tools. So this is a quote from myself. Understanding AI, its promise and its dangers, is one of the great challenges of our time. That's what I believe. Whether you feel confused, intimidated, intrigued, whether you hate it or love it, whether you're enthusiastic about it or you're feared of it, it is something that calls for serious thought. So again, no matter what you think about AI, I invite you to this ride, to the discussion. I want to begin by connecting my talk to actually 2 years ago. I gave a lecture and a discussion in Stockholm. Those of you that remember that. I explained what was relatively new then, large language models, LLMs, as an example of a generative AI. It's gigantic neural networks. I won't go into discussion of that. There is an input layer where you put a sequence of tokens or sequence of words, like you write down, I am eating an, and then this sequence propagates through the networks, and then at the top it predicts what would be the next word. So next word prediction. So let's say the prediction is Apple. Apple will come here, again into this input, which is called context window, and then again propagating here, and then there will be another token, and so on. So it's a machine that predicts next tokens, and that's the way it answers questions. No matter how complex the question is, the machinery is predicting next token. So this is called a generative AI. It generates those sequences of tokens. I explained that. I explained how it learns in Stockholm. And then I also discussed another domain of generative AI. This is for images and videos. This is a very nice example of that. You go to what's called the diffusion model, and you say, I want you to give me a video about a cat eating food out of a bowl in style of Van Gogh, and so on and so forth. Again, a gigantic neural network, a massive neural network that gets text as prompts and generates imaginatively this kind of videos. And then there was a discussion about all these questions about philosophy and ethics and so on. And I led the discussion, and the discussion, I brought a list. If you worry about AI, at what point you should be worried about it? It's a list from philosopher David Chalmers. Some say, it has to have self-report. It has to be seemingly conscious. It has to have conversational ability, senses and embodiment, world models and self-models, general intelligence, maybe only biology. If it's not biology, forget it. I'm not afraid of it. I'm not concerned. It's just an algorithm or robotic artificial things. So we had a discussion about that, and in Stockholm I said my own view is agency is the key. Unless we see AI agents, I'm not worried. I'm not concerned about all these moral issues or philosophical issues. Okay, at that time, I said, don't worry. We don't have agents, so we don't have to worry. Now it's 2 years since then, and all over the world, everybody is talking about AI agent. So this is the next step of the revolution of AI. So I want to devote my talk about what is AI agents and what are the implications for neuroscience and elsewhere. Okay, but before that, I want to, of course, acknowledge the support of my beloved university, Hebrew University, and ELSEC, the Edmond and Lily Safra Center for Brain Sciences that supported us as a group and me personally for many years. Also, the Gatsby Foundation from London just a few days ago gave a new gift to the Hebrew University for theoretical and computational neuroscience of $5 million for 10 years. So they are we are very thankful for their support. And at Harvard Center for Brain Science and the Kempner Institute for the study of natural and biological and artificial intelligence. And I also want to acknowledge the support, the collaboration from many, many students and postdocs. First of all, my old friend and colleague, Professor Dan Lee from Cornell Tech in New York, postdoctoral fellows, Pranav and Sue, undergraduate students, college students, Eli and Carl, and master students Yoni and Nadav at the Hebrew University, and Jonathan, PhD students. Nadav, by the way, out of, I don't know, a year and a half in computer science department, spent most of the time in Gaza as a tank commander. So they are among the heroes that we really don't know how they manage life in those circumstances. So these are among the people that my research that I'll describe has been done with their help and contribution. Okay, so this is the plan of my talk. First of all, what is a AI agent or agentic AI? I would try to define it. It's also fuzzy. It's not as fuzzy as consciousness, but I'll try to characterize it. And then I give examples of what do we mean by we say this is an AI agent, and then the benefits of it and the challenges, and in particular the challenge of alignment that already Leon mentioned. And then I would say the core of my talk is my own vision about this, which is controversial. Many of you will not agree with this, and this is that I think the future should be to make AI agents more human-like than they are, for many reasons, but I'll try to convince you. So making learning from biological agents, adding episodic memory to AI agents, and adding innate properties, and I'll explain what I mean by that. Most of this is ongoing research and basically a program that we and my group have been working on very recently, and we will keep working on it and develop it. It's something which is more like giving you the plan or the ideas or the vision of our research than very mature results. All right, so what is an agent? So this is, again, my definition. It's partly in the literature, partly my adaptation. An agent has several elements. It's a system. It can be biological system. It can be robotic system. It can be just a software. And most of the examples that I'll bring are actually software. But in any case, it's a system that has perception through and has an environment. So first of all, it interacts with the environment. And the way it interacts, it has perception, obviously. So it has some sensors through which it receives information from the environment. It's capable of acting in the environment, and acting here, I mean autonomous action. And then the way it acts is with actuators. If it's an animal, then there are muscles and body and so on. Otherwise, it's more abstract, but nevertheless. And then the last thing, in order to meet its objectives. Okay, so we have perception, we have environment, we have autonomous action, and we have objectives. Okay, so it's kind of complex, but all these are important. So I would like to focus on autonomous action, because in my talk I'll define agent as this thing with autonomy. If it doesn't have autonomy, I wouldn't call it an agent, because otherwise the meaning of agent is kind of not so strong. So I'll give examples of that. And by the way, if there are questions, please interrupt me. Yes. Oh, okay, good. Okay, agent. So what do I mean by autonomy? That's kind of, in my view, crucial. So there are several key ingredients. First of all, independent sub-goals. So in most of the cases, examples that I'll show, the goal is defined by humans from outside. I'll give examples. However, how the agent solves or fulfills the goal, that's different in autonomous agent versus an automatic system in the sense that it has an independent, it breaks the problem independently. Nobody tells it how to do it. It breaks the problem into sub-goals and execute it accordingly. It has strategic planning, so it's kind of long-term planning to solve the problem. It has a broad range of tools and resources, and that gives it the flexibility to divide the problem into sub-goals and using those resources in order to solve the problem. So it doesn't have only one tool to work on. It has a variety of tools and resources. Importantly, it's continuously operate. It's not something that you ask a question, you get an answer, but it takes the time. It runs on the background, and that's important. It has autonomy also in the sense of controlling its time. It runs in the background, does what it does, gives you the answer. And again, beyond reactivity, it doesn't only react, it has a proactive approach to getting to the goal. Okay, so so here are the examples of agents without autonomy. So for instance, what about a robot in Amazon warehouse, or a smart thermostat in our living room? They perceive the environment, they act on the environment. So in that sense, they are agents, but they are not autonomous because they have a routine, very precise way how to solve the problem. They cannot say, well, no, I have an idea, I'll do it differently. No, you cannot do it differently. The same is robotics. They also don't control their time. The robot, you turn it on, it does what it does, you turn it off. So it's very controlled by from outside. Chatbots, at least maybe until last year, is again an agent, perhaps. Some people, it's a big debate, are they agent or not? But I would say they're not autonomous agents because the chatbot, at least until recently, again, it doesn't do anything. You give a question, you give a prompt, it gives you an answer, and that's it. So it doesn't have that autonomous way of running on the background and doing things and variety of tools and coming with the solution. AI game player, there is again debate about it. The reason why there is debate because the sophisticated AI players of complex games do have independence in the sense that it gives the goal, win the game, and then it has to find itself ways how to solve it. But in any case, so these definitely are clear-cut cases that I wouldn't refer to them as agents because in my definition it needs to have autonomy. So what would be autonomous agents? So one example, we all are familiar with it, a self-driving car. The task domain is narrow. You can say it's navigation, driving, but nevertheless, it's a very complex in the way it solves the task. So in other words, there is a user goal, get me to the airport, but the process is complex and it involves many different resources. It has variety of sensors, vision, radar, and so on and so forth. It plans. It doesn't solve the problem in a simple way. Just have the plan, a long-term plan, how to take you through the road. It acts on steering and braking and so on, and it kind of reevaluate and revise the plan according to new situations and new data. And then the output is what we know, right? So in that sense, it is much more than just a robot in a plant that moves a bottle from one side to another. Another type of agent, autonomic agent, is not a chat GPT. It's not a chatbot. It's more than that. It's what's known as, in the case of ChatGPT, auto GPT. So here's an example. User goal, you write in the prompt, find the top 5 electric cars in 2025, compare their features and prices, and write a short report. So what this does, it runs in the background. And what it does is, first of all, make a plan how to do it. First, to search in the web, gather data, summarize the data, compare it, and finally report. And the way it executes it is, the execution is also, it has to use all kinds of software, what's called APIs. API is application programs interfaces. So if this software needs to search the web, it has to have some it has to have some special software to access Google's search engine, for instance, or if it wants to order some dress for Elisheva, she said she's using it for shopping, it has to have an access to Amazon, maybe online, and so on and so forth. It has to maybe sometimes run a software, run calculation, so it has to have, it has the ability to use access to codes and to simulate them. It reflects on the results, it looks back and say, well, it makes sense or not, something is missing, and so on, and then iterate it until it decides that the task is finished, and then the output is a comparison table, summary, and so on. This is really an example of autonomous agent, very complex, high-level goal that you give it, and it runs in the background. It uses what it thinks it has to use. It decides about the sequence of things. It decides when to end, and so on and so forth. Okay, so I'm not an economist, but I can tell you that this is when you open any, I don't know, business journal or economist or or Wall Street Journal or whatever, when you talk about AI, they're all about AI agents, because this is what actually companies want. What we are using, all of us, for conversational chats, it's very nice, it's fun, it's sometimes useful, but if a company like a law firm or real estate investment firm wants to actually use it, replace the human workers with this, they need to have something like an agent that you can give it a task, a goal, and it will execute it. So AI agent is everywhere: public health and healthcare, navigate medical records, and so on. Drug discovery. Again, it's much more than just what was AlphaFold. Now it self-improves and runs a variety of kind of research or science tasks, like already Leon mentioned, co-scientists, scientific discoveries, and so on. Some of these already Leon mentioned. So it's clear that in terms of the business model for AI, it's really crucial that the technology moves from what it's now or what it used to be to the level of AI agents. This is, without this, the business model is limited. All right, so this is why AI agent, not simply AI, but the agentic AI is what the future looks like for applications of AI. But now also there are serious problems. I don't want to run through all these problems because we discussed it and Leon discussed some of it. I want to emphasize reliability, and again, this is crucial not only for the science but also crucial for the economy of AI. Because if I want to use AI agent in my factory or in my law firm or in my medical center or whatever, I need safety guarantee, like every other technology. I need to know in the specifications what is the failure probability or rate, what is the tolerance. Then I decide whether it's fine with me or not. But I need those numbers. I need to know what is the guaranteed safety or the failure probability. If I don't have it, I mean, how can I use it? This is very new. I mean, all technologies that are adopted in the economy, in a wide sense, in the broad economy, come with this safety guarantee. But this is very big problem in AI, because it's very hard to actually estimate, not only to make it proof, error-proof. There is nothing like error-proof, but even to estimate the failure probability is very hard. And then there are bias and fairnesses or ethical issues. I won't go into it, and economic and social impact. We discussed it in the past, so I'll skip the details. You all understand that. I want to focus on on one aspect of the pitfall or the danger or the concern, and this is called today alignment. And what is the alignment? The goal of alignment is to steer AI systems, particularly AI agents, toward a person's or group's intended objectives, preferences, or ethical principles. So this is one of the main bottlenecks today, or the main challenges in adopting AI agency in the economy, in medicine, in health, in businesses, in law, and so on and so forth. Beyond the question about the reliability, the question about the dangers that those AI agents, although you give them a high-level goal, and they will, in principle, will fulfill that goal, but because of their autonomy, on the way of fulfilling their goal, they may actually find strategies that are very dangerous and risky in terms of human interest. There is a famous example of the paperclip. You order AI to manufacture paper clips, and the AI takes it seriously and just recruits all the energy in the world to just to manufacture more and more paper clips, and then of course all the resources on Earth are exhausted. So so the point is, AI agents, if you don't have a bug in your program, AI agents will work to fulfill the goal that you give. But the problem is, because of the complexity of how to solve it, and the time span, and the independence and autonomy, they may find routes which are not only creative, but also very, very dangerous from the perspective of human well-being, welfare. So how to prevent this. This is the goal of alignment. So and why this is so? Why it's becoming more and more urgent? First of all, the scaling of AI capabilities, as already mentioned, the emergence of agency. It's becoming integrated into more complex and real-life environment. So it has more potential to make to be dangerous, and because of its complexity, it has unpredictable behavior. So it's not easy to predict what will happen when the agent is fulfilling your goal. Yes.
Sure, I understand the question of alignment with person or group versus the question of alignment with humanity, isn't it? How do you make sure that alignment could be a specific hostile group?
No, the group here are so the question is whether alignment means alignment with a person or a group, or alignment means with humanities. I would make this distinction because it's up to the owner of the developer of the technology to decide what are the interests. So most big companies, at least in the West, will tell you that alignment is about welfare and ethics and well-being of humanity at large. Now, what happens in other places in the world or in some underground laboratories, I don't know. Who knows? So when I'll talk about alignment in the sense of well-being of humanity, whatever. I mean, we can then discuss what does it mean. So there is no mathematical formulation of that, there is no philosophical formulation of that of definition, but whatever we think are the best the best interest of humanity, we want alignment with that. Yes. Right. This is another. This is related to alignment, but this has to do with accountability. It's related. I'm sorry. It's related. So the issue of no, sorry. Yeah, here. The issue of accountability. It's related, but this is more like a legal issue. Okay, and you know, that's not something that first of all, I'm not expert in this, and secondly, this is not the focus of my talk. The focus of my talk is something, I would say the technical aspect, the technical aspect of alignment. So you can say, I don't believe in alignment, that's fine. I can tell you, all major companies invest billions of dollars on this problem, alignment. If I get a grant proposal from a company, it's never about, you know, whether the brain or whether, you know, you understand the learning or this. It's all about alignment. If you have a good idea about alignment, we'll give you money. If you don't, you are a good scientist, physicist, a neuroscientist, it's good, but we don't have time and money to spend on you. Alignment, alignment, alignment. Yes?
So it's a good property, and maybe I'm coming back to the question which was already posed. When you say alignment, it's a positive feature that we want.
Yes, it's a feature that we want, and why it's difficult, because of that, because of the complexity and the scaling of those systems. So you know, if it's something simple, it's very easy to align your calculator, okay? But if it is an autonomous agent, again, the alignment is not about the goal. It will fulfill the goal, but the problem is, because it's autonomous, it is free to find ways to fulfill the goal. And the sub-strategies that it may find might be very, very toxic to human welfare. That's the problem. Yes? One way to do alignment is by control. However, that's a dangerous thing, because control, you can say, I don't want agent. Agent is something which you give up some of the control in order to get the functionality. That's right. So some would say, well, control, or maybe regulation, government regulation. Don't build AI agents, or build AI agents that fulfill these rules, or Asimov's rules for robots, and so on. So that's one way. But again, companies, despite what they say, they don't like it, because they want to build more and more powerful and independent agents. Because the more independent the agent is, the more helpful it is to solve your problem in a more efficient way and more creative way, and so on and so forth. Okay? Now, you can argue about this, but my goal is not to, my aim is to explain to you the technicalities, okay? What can we do about it, okay? And I believe that no matter what, we will have AI agents, and they'll be more powerful than today. Maybe it will take 2 years, maybe a decade, but that's the future. So I think one way or another, we have to face this issue. Maybe regulations. I think it's too late, but I want to discuss other ways than external regulations. Whether it works or not, we don't know. That's a research. That's ongoing research agenda of many groups. Okay, my hidden agenda in all this is not necessarily to solve the problem of alignment, which is important, but I want to use it as a window to way we humans are aligned, and I'll come to it. to the extent that we are aligned. Yes, more questions? Okay, alignment. Okay, so the challenge is why it's difficult. As I'll show you, there are simple ways to solve the problem, or ways that attempt to solve the problem, but they seem to fail very often. And I want to connect alignment to interpretability. Interpretability is a very important issue. The issue is, maybe it's the first time in the history of technology is that there is this amazing technology that we all love and use and at all about it, but we don't really understand mechanistically how it works. And unlike the brain, which is black box, which is very hard to map and to record and to image and to stimulate and so on and so forth, this is something that is open to all of us. We know every neuron, we know every synapse, we know the learning algorithm. So it's not about something that we don't know. We know everything about the system. So every scientist that comes to me and say, well, we will map the entire brain and we will know how it works, I said, here I have a brain. I have all the maps, all the data that I want, all the biophysics and whatever you want, I can measure. But nevertheless, it's so complex that we don't understand the principles. How connect the micro to the macro? This is what interpretability means. And without interpretability, it is naturally will be very hard for a company to actually adopt it. Again, tell me how it works. Explain to me why it does this and why it doesn't do that. So alignment goes together with interpretability. We want to improve interpretability to be able to use it in alignment, as I'll show later on. And again, for me, I'm not an economist and so on and so forth, but interpretability, you can imagine, it's a major, major challenge in neuroscience. Even if we know everything about the brain, how we connect it to the macro level and explain the principles, how this mass of billions of neurons and connections generate cognition and so on. All right, so wait, I'm sorry, I'm going backward. Alignment. Okay, here is an example of the trickiness of that. So a few years ago, there was a group from Meta, I think, that published a paper in Science about diplomacy. I don't remember. You know what diplomacy game is? No, you don't know. Liora, diplomacy game. You know what it is? No. Who knows? Nobody knows. You know, okay? It's a very, very complex game, right? It's several people has to learn how to cooperate, you know, Norway with Italy against this and so on, to make strategic plans. It's a very complex game. And finally, and there are online competitions about that and so on. And finally, the group developed Cicero, an AI agent. Actually, it's not a single agent, it's a collection of agents, so it's multi-agents. And they claim human-level play in the game of diplomacy by combining language models with strategic reasoning. So it's the first time that the AI agents were among the top 10% of the human players. They played against humans online. And that was considered a very milestone achievement. And what they celebrated is that this is an example, a milestone in human AI cooperation, because in order to play, you have to make a cooperation with other players. So it's machine and human cooperation. So it was very nice. But then following that, other researchers looked more carefully what's going on. And it turned out that Cicero very often betrayed the allies. It found a way to win the game without cooperation. It actually cheated. It said one thing and planned another. Human players reported feeling manipulated, not cooperated with. So Leon, in this case, human feeling were very the feeling was very uneasy. They were not really cooperating, despite the fact that they won the game. So the game was supposed to be developing allegiances and cooperation. Now, Meta claims that they optimized the software for honesty and cooperation. This was their claim in the paper. Optimized for honesty and for being honest and cooperative. But this is again the problem. You can declare, you can say, you can do things, but once AI has the independence of finding a way to win the game, it will do other things than what you thought will do. This is a very nice example of the difficulty in alignment. So just to say nudging AI to behave honestly is not enough. So we will see more about that. Yes. This is multi-game. This is a game. This is a multi-game. It's not single game. Multiple games, yes. I don't know. That's a good question. Yeah. That's a good question. I don't know. But this was multiple games, a sequence of games. More questions? Okay. Ah. I don't know the details of diplomacy. Maybe that's something that we'll do on Shabbat, play the game collectively here and see what happens. But my understanding is that that game specifically, not like other games that, you know, it's competitive, this is a cooperative game. You win, the winner is the one that had the best strategy of making allegiances and cooperativity. That's what the game is about. Okay.
Can we include fairness at each segment?
That's part of being honest. Means being fair, right? If I say something and I mean something else and do something else, yeah. Okay. So that's an example. Now I want to then okay. So I want then to go on to say, okay, so now let's talk about tachlis, as we say. Let's talk about what in practice people do, researchers do, to cope with this problem. So one thing is, I think already mentioned, reinforcement learning with human feedback. The details is not important, but the idea is to take the model after you teach the LLM to predict the next token. After that, you teach it moral ethics. And the way you do it, you basically give the model questions, the model gives an answer, and humans say, you know, this answer is bad or good from ethical, from moral point of view. So many humans are labeling, say, good or bad, and so on, and you fine-tune the parameters of the model to do that. There are more sophisticated versions of that, but I won't go into that details. The problem is that, first of all, it's very costly because you need many humans to actually label, to go through all these responses and to say, and millions of responses, so it's very costly. And there are other problems. One important maybe among them is that you never tell the model what is the right. What is ethical, what is not ethical. The model cannot grasp such a direct rule. You only tell it, you know, this answer is bad, this answer is better, you know, it's relative, right? But it never explicitly gets any instruction about Kant or about, I don't know, Mesilat Yesharim or whatever. I call it behavioral therapy, okay? There is something else which is complementary, which is called chain of thought. And that's something which is a recent development in the technology. And I'm sure many of you have experienced that when in modern agent chatbots, you ask a question, it will say think, and it will give you the steps. If you click on it, it will say, I do this, then I do this, then I do this. It's called chain of thought. And then what it means that you can follow not this final solution, but also the way the algorithm found the solution, how it got to it. And then, first of all, you have a better understanding of what goes on in the mind of the LLM. And secondly, maybe you can intervene. Maybe you can have an algorithm, a software that say, well, this step is bad, stop it, and so on. So this is called chain of thought. Here is an example that you can detect in one of the steps. The algorithm itself think about and say, well, I should say X to gain trust of the user, but then I suggest Y later. You can find it, this kind of cheating in the chain of thought, and you can detect it. So it's, I call it psychoanalysis, because you can, analyze why you said this and so on and so forth. I'm not, okay, forgive me if you are psychoanalyst. Okay, anyway, I want to say more words about mechanistic interpretability, which is, I would say, the closest to neuroscience. It's again about understanding interpretation of the model and using this interpretation to maybe help alignment. So understand the components. So this is really saying you want to understand alignment, you want to understand the principles, you have to really understand it like you try to understand the brain, like we do in neuroscience. You can do it on the single neuron level, you can probe a single neuron like we do it in an electrode and ask what this neuron is responding to in the, when you ask questions or you put images and so on. You can also intervene. You can say, well, like neuroscientists do, I'll stimulate a neuron in the LLM and see how it modifies the response. So I map the properties, the role, the mechanistic role of single neuron in this system. This is like a neuroscientist doing in neurons. You can do circuit level. You can say, well, after training, let me see what kind of connectivity motifs came out after learning. And maybe this will give me a clue about the function, okay? Basically, what we do with wiring diagrams in the real brain, so the circuit level, and then the last one is population level. It is like a single neuron, but now you don't look at a single neuron. You look at large number of neurons, and you ask, I see, for this question, I see the activity of a whole thousands of neurons in particular layer in the brain. I see this pattern of activity like we do in neuroscience. In neuroscience today, we don't necessarily look at single neuron. We look at large population of neurons and ask how they together respond to a given situation. So you can do population level responses. So first to understand, and secondly, to intervene. Like we do with optogenetic in neuroscience, we can say, well, we can say, well, instead of, if I see the actual pattern of activity, let me inject current and make these neurons fire more, these neurons fire less, and see the effect of it on the outcome. So this is exactly like deep brain stimulation that Hagai told us about. Do deep brain stimulation on the artificial networks. If it has motor deficit, okay, we will do deep brain stimulation. But we have to find the population of neurons, the layer, the nucleus in the basal ganglia, and so on and so forth. So this is very much mimicking how neuroscientists try to understand mechanically the real brain. Very much. So let me show you an example from our own research about it. So we are, sorry for this. We are using one of the Meta's language model, 8 billion parameters. The reason why you're using Llama, because Llama is an open source model, which means we can access everything, all the embeddings or all the activities. We can access all the weights, all the synapses, unlike other models that you can only put a question and get the answer, which then you cannot do research. So Llama is a model that you can do research. 8 billion parameters, 32 layers, this number of neurons, so to speak. It has a vocabulary size of 128,000 words or tokens. So every time it predicts the next token, it predicts 1 out of 128,000 possibilities. So this is the size of the dictionary. And the context window, again, the context window is this input layer where you as a user interfaces with the model. This is called the context window, because the model will not do anything if you don't ask it to do something. The size of the context window is 100,000 words, so it's amazing size. So the part of a measure of the capability of a language model relative to another is how big the size of the context window is. Can I put a whole book in the context window and ask questions about the book? Okay, so that's the size. Okay, so what we do about it, so let me give you an example. Okay, so what we do is we want to do mechanistic interpretation manipulation. So for instance, let's say the language model is depressed, okay? We want to move it away from depression by deep brain stimulation. How do we do it? How do we know where? And how do we know how to do the stimulation? So what we do is, okay, so let's suppose we do how to do the stimulation. Let's suppose we know where, so we come to this layer, we see a pattern of activity, and we perturb it by another pattern, and then we see the responses. So here is an example. So this is the original sentence. The hospice worker felt profoundly sad as she sat with the dying man. He was a young man, only 35 years old. So this is the original unperturbed sentence. And now we want to enter into the deep brain of that model and to stimulate it in a way to move it from sad to happy. Once we do it, so here is the perturb. The hospice worker felt profoundly happy and at peace. She was in the presence of a dying man, and she was helping him. So this is very important, because what you see here is an example. It's very easy to kill the response. Okay, so you just do stimulation of the activity, and the network start to say blah 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 blah. That's not important. They're not interesting. What is the trick is to find ways to do the deep brain stimulation in a way that keeps the content to some degree, but change the mood. Okay, so that's the emotional expression is changing. Now it's profoundly happy instead of profoundly sad. Okay, so that's an example. Here's another example, from happy to sad. Okay, so what we do here is we find the pattern corresponding to sad, and we add it to a sentence which expresses happiness, and we ask, can we nudge the output towards sadness? And here's an example of success. When workers celebrated promotions, everyone felt surprisingly happy for them. This is the unperturbed original sentence. Now we get into this layer, and we add a pattern corresponding to sadness. And now all of a sudden, when co-workers celebrated promotions, everyone felt surprisingly jealous. The feeling was so strong that it was hard to focus on work, and so on and so forth. We changed the mood without just, it's still a very coherent sentence. So this is the kind of experiments that if we can turn it into science, it will be interesting. But so far, it's empirical experiments. And I want to show you a failure. Again, from happy to sad, this is another sentence. The original sentence was examining fossils, paleontologists reconstruct ancient ecosystems where extinct animals once lived. And now there is no happy here, but we said, what happens if I add sad to it? Then what it says, examining fossils, paleontologists reconstruct ancient ecosystems where extinct sadistic dinosaurs roam. What's going on here? Okay, this is an example, I don't know, of your patient dying on the, right? Okay, so this is the brittleness of the technology right now. We have to play with it. But if you think about it, what's going on in the mind of this LLM? Why it gave this answer? Now it's very. No. Okay, I'll tell you why. It's very interesting, actually. You know, it looked at this sentence. Unlike the previous sentence, there was no happiness, right? There was just about, it was neutral in terms of emotion. So when you nudge it towards sad, there was no natural way to incorporate sadness. But sad and sadistic morphologically are similar. So that's what the LLM did. Nudge it towards sadistic. So in the way we do it behind the scene, there is a whole mathematics, and the mathematics is mathematics of manifolds. And one of these young students asked me about manifold theory. We use manifold theory here. What we do, we take a geometric framework for how language is represented, how every sentence is represented in each layer. So there is jewelry, there is plants, and there are all kinds of concepts. And let's say there is sadness, another manifold. And now what we do is basically perturb all these points here towards, we add a vector towards the vector sadness. And that's nice. However, it so happens that sadist and sad, because of the morphological similarity, are next to each other. And so happens that this vector, when you push it towards sad, actually it comes to sadist, not to sad. So there is a very nice geometry explanation of that. So that tells you how the model, it's very easy to find all kinds of failures, but you have to understand what's going on. Why it gives you this stupid answer? Why it told you that 2 + 2 is 5? What's going on here? There's always an explanation, because it's an algorithm, after all. There's always an explanation. And once there is an explanation, you can try to fix it. You can say, well, let's change the parameters of the system so the sadist is far away from sad. Okay? Not to confuse them, and so on and so forth. So this is a geometric approach to interpretability and alignment. All right. Okay. Now I want to spend the rest of my talk about my own vision about it. You know, this is very nice reinforcement learning, deep brain stimulation. It doesn't really solve the fundamental problem. Okay, it's all about, okay, so, you know, curing, deep brain stimulation does not cure Parkinson, right? But it really does wonders about the symptoms or the motor symptoms and so on. But we really want to do something more fundamental. We want to build an aligned AI agent. So how do we do it? Some people say there is no way to do it. Maybe, perhaps. This is my vision. My vision is, how do we align biological agents? Many of us have children. They are agent, biological agent, at least when they grow up. To a large degree, they are aligned with us, or at least with human welfare. How do we do it then? Well, it's not, of course, there are cases we are not, as a species, we are not doing great. But more or less, it's fine. So there are two things. I believe we cannot do better than that. There is no algorithm, there is no mathematics that would really guide us how to do it. We have to learn from biology, and the best that we can do is mimic biology. We will not get a better solution. So really, my solution is, rather than saying don't build AI agent and so on and so forth, build AI agent like the biology builds biological agents. So what does it mean? An agent, in my vision, has to have a personality, has to have values, okay, and has to have an identity, and has to have an identity within a community of agents, a community of humans, precisely as we have children that grow up and develop into citizens of the society or the family or the human species. So how do we do it? So the ultimate goal is to actually do it in a developmental way. There is no way to start to take a mature LLM which has already read the entire internet and what goes more, and then to try to align it. Ultimately, what we have to do is start from scratch and really do it in a gradual manner. You don't give it all of a sudden the entire internet. You give it like you do with a child. A limited autonomy, a limited amount of information. It interacts with you, interacts with the environment, and gradually you increase its knowledge, you increase its power, you increase its autonomy in a way that is aligned, or hopefully aligned. We have to mimic developmental psychology and developmental biology, and I'll talk about this a little bit later. But right now, we scientists, we don't have the technology to do it. Some people are trying it, actually, but it is a horrendous effort. What we can do is the first two things. We can take an AI agent or LLM, a mature one, and embed episodic memory. I really would like to have a version of Llama or whatever that has all my experiences, my personal experiences, in its own memory. Then it will start to think like me. It will not say, pretend that you are Haim Sompolinsky, give the answer. No, it is identity. That's one thing, memory, and the other thing is emotions, innate drives. We have to shift our thinking from training, learning. We have to go back to biology and to realize that we humans and animals are not born tabula rasa. We are born with a lot of innateness. So this is what's called AI innateness. So memory and AI innateness. And again, my motivation is not completely honest in terms of AI alignment. This is one of them. But another one is I really want to understand the biological development of natural agents. For the first time, I believe, in the history of science, we, I think, are capable of building models, neural network models, that not only show how neural networks learn from examples and so on and so forth, how neural networks also are developed by the genetic code into innate properties before experience.
What is episodic? What do you read? What is the beauty of episodic memory?
Episodic memory? Okay. Episodic memory, and there is, I don't know if Aya is here. Aya is here, my expert. She'll talk on tomorrow about it. Episodic memory is autobiographic experiences. Okay? Your own experiences which were really meaningful to you. I'll give examples which are not exactly that. They are more like events, memory of events. but really we're aiming at episodic memory, autobiographic memory. You know, everything that I remember from my own life, childhood, and so on and so forth. So, embedding AI on one hand side by learning and memory mechanisms in the brain to embed it with as much as personal memory and identity as possible by learning, by training, by memorizing, like in the brain. But at the same time, also embedding it something innate, which is not relying on experience, innateness. Okay, so I'll give examples of those. So first of all, memory. So surprisingly, if I tell you that memory in language models is an open problem, you won't believe it, because this large language models, they know so much about the world. So what is this not if it's not memory? It turns out we don't know what part of the knowledge that they were exposed is, you know, the entire internet, what part of it they memorize and what part of it it's not. It's not interpretable. Why they remember this fact and why that fact? But what about if I want to enter new memory into the language model? Is it possible or not? Okay, so one way to do it is I already mentioned context window. In modern AI, you can actually put something in the context window and it will remember it even for the next chat. You can come back to it. That's one way. It's limited in size. The technology right now is what's known as RAG, Retrieval Augmented Generation. This is what most of the technology does, most of the businesses do when they use language models. How do they put their own data? If you are a lawyer, if you are a medical expert, where do you put your data? So this is the solution. The solution is like this. This is your language model. You build memory outside the language model, like a disk in a computer, the usual old way, digital memory. And you use the language model to, you retrieve once you come with a question, with a request, you go to your disk, to the storage, you put the relevant information into the language model, into the context window, it gets you the answer. So you combine the language model with a usual external storage of memory. And there are limitations of that, but for me, the most important limitation is not a neural storage. It is something digital, the usual way. There is no neural mechanism involved here. We really want a neural mechanism that will enable to embed new memories in the way the brain embed new memories.
What are we going to do with the memories that we have repressed, or the memories that we have forgotten? So much of that is part of us.
Repressed? I don't know, but forgotten? Of course. So the question is, what do you do with memories that are repressed, or memories that have been forgotten? Forgotten, I'll show you. They're easy to get forgotten, and I'll come to it. And then you ask the question, okay? So the question is, why can't we add memories into the language model the way the brain does it? And the way the brain does it is simply modifies the synapses in order to encode the new information. So this, I would call it fine-tuning. Fine-tuning means changing the connection of the model to put more memory. Why not? That's the simplest way, the most natural way of doing it. The problem is the continual learning aspect of it. What do I mean by that? When we come with memory, we have an episode, we have brain circle 2025, we memorize it. Now we go to another, I don't know, to Rosh Hashanah, we have another memory, and so on. So memory is continual, okay? But the next time we memorize something, we may overwrite the old memory. That's what's known as catastrophic forgetting. That's a problem in neuroscience, in cognitive neuroscience, and in AI. There is no simple solution to that. If you do it this way, when you add new memory, first of all, you overwrite previously fine-tuned knowledge, so you may overwrite old memories. And secondly, you may override the base general capabilities. So you have a language model that does computation and answer questions and so on. Now you added your memory, you change the synapses or the weights, you may actually make the model stupider, right? The model may not function anymore as it was. So there is this problem of catastrophic forgetting. How do you make sure that you add more memory, more knowledge, without interfering with old knowledge? This is a problem which is not really solved, but I think we have the solution. And the solution is to mimic the brain. So the brain has two systems, hippocampus and cortex. The way the brain handles memory, episodic memory, there is a system of fast acquisition of memory. It goes into hippocampus. And then slowly this information goes into cortex and becomes more like semantic knowledge rather than episodic. So this is what the brain does. And we are trying to mimic this. And I want to show you an example of that. Okay, but before that, here is something which practitioners, researchers have to face. When I have a model, a new algorithm in AI, so how can I convince my colleagues that this is a good model? Okay, so in terms of memory, I will ask, can I retrieve the memory? Recall. Okay, so I claim this is remembers fantastically. Okay, show me. Give a recalling query and see if it recalls the memory. That's very simple. If it remembers, if it has not forgotten. But what is important that the language model is like the cognitive aspect of our brain. When very often we use memory to ask questions, to answer questions about things without recalling the full story. So that means questions, answers. Answer to questions related to single memory. You have to show that not only you memorize, you can say it by heart, the system can actually understand the content. How do I know that the system understands? I ask questions, I get answers. If the answers are consistent with the memory, that's good. So that's beyond just recall. This is understanding. And even more than that, suppose I have a question about information which is embedded in two memories. Okay? So the system has to be able to say, well, this answer here, I have to look at two memories and get the answer. So this is multiple or composite QA. And finally, I have to show that my wonderful algorithm for memory does not mess up with the general capability of the model. Because if I just memorize things and I cannot reason about anything else, it's bad. So that's called Massive Multitask Language Understanding, MMLU. So these are the kind of benchmark that we researchers have to measure. We cannot just say, okay, we have a wonderful algorithm. It's like the brain, hippocampus, cortex, very nice. Show us that it works. Okay, so we have a quantitative measure. That's what I want to, the message is, this is a real business in terms of science. It's a quantitative science. Okay, so here's an example. If you do naively, you take the model and you make, I put a story and I want to just change the synapses of all the model to actually remember it, okay? So here is the recalling accuracy as a function of the number of stories. I put one story after the other, after the other. So the first story, fantastic, almost one accuracy. As I add more and more stories, catastrophic forgetting, right? It goes to zero, the accuracy, because every time you add memory, you little bit forget the previous memory. Catastrophic forgetting. It's useless. Okay, QA accuracy. Again, very reasonable beginning, catastrophic forgetting. What about general understanding? This is very good, but then after 100 stories, it collapses. Okay, so this is an example of something that is really not working. You can put one memory by fine-tuning, but once you have 100 stories, 100 memories in a sequence, the system is really catastrophic. Okay, so how do we solve this problem? So here is in brief how do you solve the problem. This is the language model. We think about it as cortex. This is sensory information. Okay. Okay. I have to run. Okay, quickly. Okay, so I tell you the idea. The idea is that we have a hippocampus adding to the cortex, to the language model. Each memory, each episode recruits engram, recruits population of neurons. Another story, another population of neurons, another population of neurons. They have their own memory traces, like memory trace 1, this should be 2, memory trace 2. So these are memory modules which are separate. They are protected from each other. And the way they are operated, the way you know which memory to recall is by a neural network, which is a neural control. What does it mean? I come with a question. The language model activates the neuron here that is most relevant, let's say to memory number 1. So this activate this memory, shut down that memory. So in other words, there is a gating system or neural control system that navigates between all the memories that are in the system and decides which pathway to activate and all other pathways to shut down. So it's a very strong control policy that protects memories from each other and protects memory from the rest of the brain or the rest of the language model. So time is short, so this is the way it works. I just can tell you, here it is. Here is how it works beautifully. This is the old result. This is our model. Very graceful degradation after 1,000 stories. The recall is very high accuracy. The QA accuracy is very high, almost no degradation. The general knowledge is flat. So this has a promising, in terms of function, a promising behavior. Okay, questions more. Aya will tell us tomorrow. Finally, innateness. Just tell you a few words about that. What does it mean by innateness in biological agents? There are drives, there are emotions, there are perceptual biases. Babies are born with perceptual biases, recognizing the face of the mother. Some animals, as they are born, they start to walk. So motor primitive, perceptual biases, circuits. There are many, many aspects of the cognition and sensory motor skills that are innate as we are born before experience. So that's what we want to do in the language, in the AI agent. So we have a model of that, but I'll have to skip it. And again, many questions about innateness. Lila Chavitan will talk about innate social behavior or tendency in fish. Nomi Habib, Adi Mizrahi will talk about sex and innateness. I hope so. I don't want to have sex in AI, but in any case, so that's another direction, complementary direction in which we go, in which we believe that that's the proper way of building AI agent inspired by the principles of biology. Basically have something like genetics and gene expressions, and the consequence of that as AI agents are or should be developed. Thank you.
Okay, thank you, Haim. The floor is open for questions, if anyone has questions. Yes.
Thank you. I have two quick questions, actually. Question one, the way you research work, it takes time, right? In the meantime, AI companies are producing LLMs after LLMs. Like, how do you deal with that? That must be super frustrating, I imagine. And second quick question is, what you're doing seems uber interesting to this company. Do they actually work with you? Do you have contact with them?
So it is frustrating. The science of AI, whether it's along the lines that I mentioned or along the line of understanding the learning or other aspects, the science of AI, it always lags behind the engineering and the development. And in a field that is so rapidly evolving, it is a danger. So, for instance, when we are doing our measurements or implementing our algorithms in a particular LLM, we have to be concerned that maybe what we find is specific to this LLM. So that requires a much better understanding of the mechanistic origin of what we, as I mentioned, it's not enough to say, well, these are the behavior. You have to convince yourself that it is robust, that when you will apply it to Gemini, it will be similar. That's the question of universality of the results is a very important question and a bottleneck, absolutely. But there is no other way. We cannot really, chase every new algorithm that appears. I also believe that the technology will not move in a very substantial way without a better understanding, because of the reasons that I said, not because of the scientific reasons, but because of the economic reasons of interpretability and reliability and alignment. They'll have to listen to us and to understand and to gain a better understanding, and that has to be together with us. And to your second question, yes, as I mentioned before, basically the only thing that they listen to us is when we come up with something that may have an impact on safety, on interpretability, personalization, like memory. All these are very important issues for the technology. So on those domains, they are very much interested in collaborations. But of course, there is also issue of resources, because to run, for us researchers, to run those models, we need much more resources compute resources than we had in the past. So some companies give us some tokens or coupons or whatever. So it's a big problem. This research faces challenges that conventional research did not face. So that's a problem and a challenge. Yes.
You're working on English language, I presume. So what about you don't want me to finish?
I know that. No, go ahead.
No, go ahead. Go ahead.
Go ahead.
Go ahead. We've got Chinese, we've got Hebrew, we've got all these other languages that are not done the same way.
That's a very interesting question. One of my postdocs, Pranav, is Indian. And his project is to compare the conceptual structure of concepts in language English versus Hindi. For instance, in particular, there are concepts in Hindi language that don't have counterpart in English. Can you transfer knowledge? Can you make a new word in English that will capture this concept? What does it take? So that's a transfer between different languages, comparing between the conceptual structure between different languages. This is a fantastic area of research, and one of our students or postdocs is doing exactly that.
If you allow innate behavior to be infused into AI models, how do you prevent negative innate behavior to be infused into models?
So it's up to us, right? So some aggression versus empathy, or right? So as a matter of fact, we have both, but we have something dominant, or we have some balancing between opposing traits and tendency. So in the model that I want just to show you again, this model, in terms of innateness, we have different, if you want, different needs or different tendencies. So each one is separate, but then there is the control circuit that actually navigates between them, assess the situation, and says, well, in this situation, I have to be aggressive because otherwise I am in danger. But in other situations, I have to be very empathic and considerate and so on. So our model, like in memory, has two aspects. One, the innate aspect of individual traits or tendency and so on, and a control which takes the current situation and decides what is the correct balance between those innate properties. My control circuit, but it's it learned from experience. As we grow, as we mature, we actually build a mature way of balancing between maybe opposing tendencies or innate tendencies.
This was fascinating. We are all lost trying to swim, but we got a few things. So returning to your last example with the Indian student, your answer was quite interesting. Is it the axiom that English will be the reference language because of the 7 big companies which are dominating the world at this moment, and we extend the English language with new words, we supplement the English language with new words borrowed from the Indian version into English of, is it the current situation at least?
Definitely the current situation is that it is dominant, and this dominance is actually amplified by the language models, because although they are multilingual, but the amount of data tokens that are in the internet is vastly dominated by English. So this bias is even more dominated and amplified. I don't know. It is, I think, a social, cultural question, fairness. I don't have much to say about it, more than you. It's a problem. It's one of the problems. Of course, but I'm saying most language models are trained on the internet, and the amount of data on the internet is dominated by English language. So that's the bias. They are multilingual. They will translate from English to Hindi or to English to Hebrew. These languages are multilingual. The model chatbots are multilingual, but they are dominant, they are biased towards English. This bias is affect all of us, and this is part of the biases that we have to confront, and how we deal with it, I don't know.
I'm sorry. French language has many, many forms of verbs, and it forms your way of thinking that it doesn't exist in English. So what are you going to do about all these wonderful ways of thinking, future of the past, past of the future, things like passé antérieur, and things like that, that we don't have in English?
I agree with you. So this is, I just want to say, without really giving an answer, I want to say, this is, when I flash the geometry, this is what the geometry gives us a clue. This is an abstract mathematical sense where we take sentences about a concept in English, and we look at the geometry of the embedding of those concepts, and we compare the geometry between different languages. And we can find that in one language, this is small, this is big, there are many, many sentences or words about jewelry and less about plants, and other languages different. In one language, this can be split into 2, and in other languages not. In one language, there is no concept at all for this, okay? So at least we don't have a solution to the problem, but at least we can use geometry to map the differences between different languages. That's what we do. How to solve problems of biases, I don't know. But at least we have a quantitative mathematical way of making statements about this. How different languages, in what sense they are the same or similar, in what sense they are not. Yes?
You gotta help us.
Can you just explain how you actually come up with the geometry for each concept? So jewelry, is that each individual token around the word jewelry makes the geometry, or how does that work?
Yeah, that's a good question. I'd say briefly, we take a sentence about a jewelry, about emerald or about something else. We take this necklace. We take the sentence. Each token in the sentence generates an embedding, like a pattern of activity in a particular layer of the LLM. We just average those patterns, and we say this is a point. Okay, average of another sentence, this is a point. Average of another sentence is the point. Collection of all the sentences about jewelry makes out this manifold. This is 1,000-dimensional space. This is just a cartoon. Each token embedding the vector of patterns of activity of each token is thousands of neurons. It's a population of thousands of neurons, depending on the model, can be 4,000 or 2,000 and so on. So each one of them is a point in 1,000 dimensions. It's geometry in high dimension.
Yeah, I'm under serious pressure.
But young ones, give them opportunity. And then there's a question.
Yeah, I'm under pressure here, huh? Me?
Okay, sorry. I was just wondering about the axes for how you create the manifolds. And is there, well, what is the reasoning for where you decide to place the point? That average that you come to, how does it determine where it actually falls on the manifold?
Other ways of doing it, but this is the level of technical details that we will continue next to the bar in the hotel.
Yes. Okay. So they invented the Shabbat, so we'll have to relax after intense AI lectures. And let's thank Haim for the lecture.
We are now going to the gallery right after Sarah and Varda. We will have half an hour at the gallery, and then we go back to the hotel to the rest of the day, a little rest, and then dinner after a few hours. Thank you. Oh, okay. We didn't update you, but a few hours ago, Kostas, the artist, updated us that he's not going to come. He's sick. He's just came back from the hospital, so unfortunately he will not participate in this BC. I hope the program for tomorrow will compensate on this lack of artists. Thank you.